Hello, physics students. Today we are going over the Unit 1, Lesson 2, independent work slides. If you haven't yet seen Mr. Mono's video going over the lecture slides, I suggest that you pause this video, open his video, finish watching it before coming here. So what we're going to be doing is going over all of the slides with green banners. While doing this, we're going to take each question step by step. If you ever get lost, you can wind the video a little bit, or you can pause it, try to work the question out on your own before continuing the video. So today's objectives, we're looking right into how we're going to correctly use scientific notation. We're going to check out how you correctly calculate unit conversions. And you're also going to correctly identify significant figures within large or small numbers. Now, to get started, we're going to go to that first slide with a green banner having to do with scientific notation. As Mr. Mono went over in his lecture, scientific notation is when we have numbers that are either very, very large and complex or very, very small and complex. And we are going to convert them into a more digestible number. On this slide, on the left, we are going to be doing conversions of numbers from standard notation into scientific notation. Over here on the right-hand side, we are going to take numbers that are already in scientific notation and expand them out into standard notation. So let's begin with letter A over here on the left-hand side. The first thing to do with scientific notation is to figure out where the decimal point is, which I just put in for you. Next, we are going to take that decimal place and we're going to move it all the way to the left to make this number between 1 and 10. So the number has to be between 1 and 10. Technically, the number has to be between 1 and 9.9. And we're just going to place our decimal place right behind that 1. So now we have a number when we type it out to be 1.004507. We have that number. Let me make it red and let me make it a little bit larger. We have that number between 1 and 9.9 or 1 and 10 now. And what we're going to do is we are then going to put our base in. And our base with scientific notation is always going to be times 10. Once we have that base in there, we then need to put in our exponent. Now, the exponent is how many times the decimal place in its original location moved. And if we move it in standard notation to the left, our exponent is going to be positive because we are making a very large number into a smaller scientific notation. So let me show you what I mean. We're going to take that decimal place and we're going to move it 1, 2, 3, 4, 5, 6 times. Since we've moved that decimal place 6 times, we are going to have a number 6, a positive number 6, as our scientific notation. And that makes this number's scientific notation come out to be this. We would write all of this as the scientific notation, 1.004507 times 10 to the positive 6th power. Now, since we've had a scientific notation where we were moving the decimal place to the left side, let's see one where we're moving it to the right. So the decimal point in this number is right where I have just placed the red dot. And now we need to move that decimal place to the right this time. And we need to move it to the right, the point where we create a number between 1 and 9.9. So that would be right here. Our new number would be, or new integer rather, would be written as 6.3. One second. It would be written as 6.3 205. And just like our previous scientific notation, our base would be times 10. Now, the last piece of the puzzle, just like before, was to figure out what's our exponent going to be? Well, our original location for that decimal was right here, and we moved it 1, 2, 3, 4, 5 times. We made this number, which was really small, it was a decimal, into a larger number. So this time, our exponent for scientific notation, since we went in standard notation here, we moved our decimal place to the right. We are going to have a negative exponent this time. So you can see that we were able to display this decimal, which was a really small decimal, as a regular integer that was between 1 and 10 with the scientific notation attached to it. So what about a huge number? One that is in the trillions? Well, letter C helps us out there. Let's take a look, huh? Let's put our decimal place in at the end where it belongs, right there. And this time we need to put that number. Remember, we need to display this number as though it was going to be between 1 and 9.9. So we're going to put the decimal place all the way behind that 2. And that's going to have our number pretty darn long, but luckily we can actually kind of cancel out those last zeros because they're not going to be a part of what we're displaying. So our new number is going to be 2.03409556. And all of those remaining trailing zeros, we can kind of just leave them out because when we're displaying a number in scientific notation, those zeros can be put back in if we were to re-expand this number using its exponent. So now we're going to have that times 10 there as our base, just like we always do with scientific notation. And now we need to figure out what our exponent is going to be. So we need to count how many times we moved the decimal place from the original location to its new location. We moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So because we moved it 12 times to the left, it's a positive exponent. So our new scientific notation would be displayed as follows. It would be 2.0340956 times 10 to the 12th power, meaning that if we re-expanded this out, we would move the decimal place in our scientific notation to the right 12 times. That would put these 5 zeros back into our number. All right, so we got another one where we're going to be taking standard notation, putting it into scientific notation. So let's take a look-see here. Our decimal place, just like before, I'm going to just put it in a little bit bigger of a dot. And I know that we need to move this right behind that 9 because just like always, we're trying to make a number that's between 1 and 9.9. So there we go, 9.14. Let me just make sure I have all of my thoughts correct here. Yep, that's correct. So 9.14. And then we are going to do exactly what we did before. It's still going to have a base of times 10 for scientific notation. This is what allows that decimal place to move in powers of 10. Now we are going to get to the exponent. How many times did we move that decimal place? We moved it once, twice, 3 times. So what we're going to do here is we are going to make sure that we are going to properly display that. We moved it to the right, so it is going to be a -3. This is what 9.14 is as our scientific notation. So all these now are done in scientific notation appropriately. The last piece that we need to do is express these numbers in an expanded form, meaning that we are going to take them from scientific notation and we are now going to put them as a standard notation. Whenever we have a negative exponent, negative exponents mean that we are going to make the decimal place go to the left. Positive exponents mean that we have the decimal place going to the right. So when we are doing this, it can get a little bit sloppy, but I think we should be a-okay. Let me show you what I mean when I say that we are going to expand these numbers out. We're going to start with letter A right here. So let's first take a moment and take a look at this number, 3.0526. What I'm going to do is I'm just going to first type that number without any decimal place at all. Let me make sure that I'm going to do this with the right ink color. So it's going to be 3 points, so no point this time, 30526. Now, you might be going, something looks wrong there. And that's because we haven't expanded this outward yet. Remember, since we have that -7, we are going to take this decimal place right here, and we are going to be expanding it outward to the left to make this number into a decimal place, into a decimal. So let's do that. 0. How many times am I going to move this? 7 times. So that means I'm going to have 6 zeros before that's 3. So 0.1, 2, 3, 4, 5, 6. And then I can write my regular number, which was 30526. And to display this a little bit further using a little bit of drawing, remember our first location where the decimal place was right here. So we moved the decimal place once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. And that makes this work out properly. So our proper expanded standard notation for the number in letter A is 0.00000300526. And although that seems really tough, just remember all we're doing here is moving that decimal place the amount of times the exponent tells us. So it all comes down to this exponent up here. In letter B, we are not going to be making a decimal place this time. We are a decimal number. We are going to be making a larger number. That is because we have this positive exponent this time. With a positive exponent, we are going to move our decimal place to the right. We could actually start doing this directly by looking and seeing how many spaces we have in our number. So we can go 1, 2, 3, 4, 5. Okay, so at the end of the number, we move the decimal place 5 times. We need to move it 8 times. So we are going to fill in zeros for those placeholders. So we have 1.1307070. And the reason why we get that number is because of these placeholding zeros right here. When we are moving our decimal place, we are trying to move it all 8 times. So let's make sure to count and see that we had it correct. 1, 2, 3, 4, 5, 6, 7, 8 times. So this number, we place the decimal place at the very end right here, is the standard notation, the number that we see in letter B. For letter C, we have another situation with a negative exponent. So once again, we are going to be moving this number. Its decimal place is going to go to the left 5 times. And if we move the number once, move that decimal place once, that means that we are now at a -4. So if we wanted to just display that as the number, we could do this. 50623. And really all we're going to be doing to that number is putting 4 decimal places in front of it. And once we put those 4 decimal places directly in front of it, we have our proper standard notation. let's just do a quick check. So we started with our decimal place right here. We need to move it 5 times, once, twice, 3 times, 4 times, 5 times. Perfect. And finally, we have this really big one. We are going to have to move this number. We're going to have to move its decimal place 10 times. So we could actually just do this by adding a whole bunch of zeros. What I would recommend to students is you type out your number or you just write it on a piece of paper, 0.04, and then you're going to fill in a 0 for every time that you're going to fill it in. So hold on, I'm going to add a bunch of zeros to the end of this number, and we're going to just see where the number will end in terms of its decimal place, okay? So I'm going to grab my pen again, and I'm going to move that decimal place. So we're going to move it once, twice, 3 times, 4 times, 5 times, 6, 7, 8, 9, 10 times right here. So the number would get cut off right here. And so we could actually just have that as our location. So let's see, we're going to have 6.04 with 1, 2, 3, 4, 5, 6, 7, 8 zeros after it. So let me type that out. 604, 1, 2, 3, 4, 5, 6, 7, 8. Our final answer should be displayed as the last number I typed right down here. And you could keep the decimal place at the end as well. So that's your scientific notation conversion independent work, as well as doing scientific notation to standard notation. Now you get to the point of converting your units. This is an extremely, extremely important part of physics is unit conversion. And what we're doing here is we're mainly going to be working with the prefixes that Mr. Mono went over in his lecture. Over here, you can see that we have all of them listed out, as well as their scientific notation that goes with them. And what you're going to do with unit conversions is you're going to take whatever number is in the question, and then you're going to put a fraction next to it. So I'm going to do letter A right off the bat just to show you how to go about this. One thing to do directly is to find what you're going to be converting. Letter A says that we're going to be converting 76.2 kilometers into meters. So the first thing I actually want to try to do is to find where kilometers is on my unit chart. And in the prefix chart, it is 10 to the third power. Another way to write 10 to the third power, of course, would be as 1,000. So 10 to the third, that's what that means right there, is equal to 1,000. And what this means to me is that for every kilometer, for 1 kilometer, it's going to equal 1,000 meters. The way that this would be written as a fraction would be if you had 1,000 meters divided by 1 kilometer. I'll put that as a fraction right there. There we go. So pretty much all the things I just wrote are going to help us in our unit conversion for letter A. So in the first unit conversion, we have 76.2 kilometers. And I'm actually going to not put kilometers in red. I'm going to be writing kilometers in, let's do dark blue. This way we know that units are going to be in a dark blue. Now, when we're doing this piece right here, you might be saying, whoa, whoa, whoa. This looks like it's going to be too much for me to handle. And it's really not. Don't worry. All we need to do is we're going to use a little bit of math. Because we have 76.2 kilometers and we're trying to get it into meters, that just means that in our fraction, meters will be at the top. So we use the same fraction as before. We're going to use the fraction I just typed up here, and we're going to use it in our unit conversion equation. So we're going to multiply this times 1,000. First off, I'm going to want to put my multiplication. Usually I don't use a letter X. Usually I use an asterisk instead. So that's what I'm going to do here. This way we don't confuse our units with our math functions. Okay, so then what we're going to do is we are going to put 1,000 meters. And remember, I'm going to always be trying to put my units in blue. And this is going to be over 1 kilometer. The reason why we're putting it over 1 kilometer is that fraction that I just made, it's saying, hey, for every 1,000 meters, we're going to have 1 kilometer of distance. Some people say kilometer. Of course, you can do that. It's kilometer or kilometer. They're totally interchangeable depending on how you want to pronounce the word. And now all we do is we're going to multiply. So what are we going to get here? Well, let's just use our calculators and let's figure it out. So we have 76.2 times 1,000. Pretty much what we're going to end up with is 76.2 thousand. And when we're doing that, we have 76.2 thousand. So it would just be 76,200. And the unit that we're ending in is going to be meters. The reason for this is because while we're doing the math here, we actually are going to have the kilometers cancel out in our equation, like this. So the only unit that we're actually left with is going to be our meters. So we take our meters and they go right there. Now, the next one is a little bit more complex. The reason for that is because we're going to be going from picograms to kilograms. And picograms sounds really scary. In essence, it's not as scary as you might think. Pico on our prefix chart is 10 to the negative 12. So if we have 76 times 10 to the negative 12, we are then going to try to convert that into 10 to the third power. So we are more or less going to be changing our exponent here. We don't really have to touch the base as much. We just have to deal with the exponent. So let me put a line across here so we know that we're no longer looking at letter A. We're going to be moving on to letter B. So what we're going to be doing here is we are going to be converting for letter B, we are going to be converting our picograms to kilograms. Let me type in our little 76.2 picograms, which is going to be small p, small g. Units, PG. And then we are going to be converting that into kilograms. So you're probably wondering, wow, we're going to be going from negative 12 to positive 3. So what I mean there is this. Just like before, when we have picograms, we have our base of 10, but our exponent is going to be a negative 12. And in this case also, we're going to be needing to think about what we have when we are converting to a larger prefix, such as the kilograms that it's requesting here. So for our picometers over our picograms, for our picograms on one side, we are going to have 10 to the negative 12. What we're trying to get to is the kilograms on the other side, which is 10 to the third. The math here is that with exponential numbers, we are just going to add them when we get an exponent like this. So if we wanted to add these together, we're going to end up with our -9. So if we're converting 76.2 picograms into kilograms, we are going to have this as a -9 number. Now, we are trying to convert these in a sense of, hey, if we have this many 76.2 picograms, how many kilograms of that would that be? Well, when we do the math, we come out with it being 10 to the -9 up here. And then we have to do a little bit more math because we need to convert that 76.2 into 7.62. The last one here is that we are going to be wanting to, let me put a line across, this way we know where we are for letter C. So for letter C, we're converting 1 day into seconds. Let's see what that's like. So if we have 1 day, and we are going to convert that day into seconds. First thing we're going to want to do is figure out, well, how many hours is that? Well, we know that 1 day is 24 hours. We just want to take it step by step, slowly. From 24 hours, we want to figure out how many hours and minutes we have. So we're going to go hours to minutes. So we're going to do 24 hours in our day times the 60 minutes that there are per hour. And when we multiply those two together, we're going to do 24 times 60. What do you get? 24 times 60, you're going to get 1,440. And that's minutes. But then we want to figure out, how many seconds there are. So we're going to have to multiply again. For this, we're going to multiply this times the 60 seconds per minute. And when we do that, we're going to figure out how many seconds are in 1 day. So we multiply that 1,440 by 60 again, and we're going to end up with 86,400. So just in this question, you break it down step by step, one step at a time. 1 day, 24 hours, 24 hours times 60 minutes. Take the total amount of minutes, multiply it by the amount of seconds. You just keep taking it step by step. Right, so our next slide is simply the measurement slide. According to the slides that Mr. Mono went over, we can always go one more step down on the measurement, or getting one more bit finer in measurement, depending on the tool that we're using. This tool right here is in centimeters, and it shows that we have millimeters. So each one of these small lines after the centimeters is a millimeter. And we are going to be trying to determine how long the green strip is. So if we place a line at the end of the green strip, we can see that it gets to 1 centimeter. So we know that we have that. 1 centimeter is there. But then there's also the millimeters that come after. Because in the metric system, we still use powers of 10, all I can say is this, that we are going to want to make sure that we are going to add that in. Oh, went too far ahead. So we want to add that in, right? To do this, we are going to add a decimal place to say, hey, we're going 1 bit smaller. And we reach the first line there, so we know it's going to be a 1. And then because we can go 1 step finer, because it's between those two lines, we can say, okay, well, it's between 1.1 and 1.2. So we're going to give it the 1.15 to say it's right between those two. You could also put 1.16 or even 1.14. There's a range that you can put. This answer is going to be 1.15, and that's because while we're stretching down from 0, we reach past the 1 centimeter and then past its 1 millimeter mark after that, and that's between the 1 millimeter mark and the 2 millimeter mark. For this one, for the second one on this slide, you can see that we have 1 centimeter and we have it going between, directly between 1 centimeter and 2 centimeters. This would be 1.5 centimeters. Another way you could find this out is if you were to count after the 1 centimeter line, you count 1, 2, 3, 4, 5. Reach 5 lines, so it's 1.5 centimeters. So now we're going to go on to our significant figures page, which we use sometimes in physics to determine how an answer should be displayed, how many zeros it should have. So all non-zero digits are significant. All zeros between non-zero digits are significant as well. All beginning zeros of a number are not significant. And all ending zeros are significant if the decimal point is written in, but not significant if the decimal point is an understood decimal, meaning that the ununderstood decimal is when the decimal point isn't there, but we know it would be. It's just not displayed. So there's no numbers that come after the decimal point, so to speak. For instance, when we say the number 10 or the number 11, those are understood decimals because we know that after that 0 in 10 or after the second 1 in 11, there would be a decimal point there, but it's just not displayed. So the independent work slide here is fairly straightforward. When we count the numbers, we can figure out the significant figures. So I'm going to highlight my cursor and we're going to go through each one step by step. Letter A is 5, 4, 3. Well, all those numbers are not zeros, so this has 3 significant figures. Letter B, all of these numbers are not zeros either. Even though there's a decimal place in there, that's fine. It's still going to be 5 significant figures. 22.437. There's no zeros. Same thing for letter C. All these numbers are not zeros. They are all significant. So we just count up how many numbers there are. There's 1, 2, 3, 4, 5, 6, 7. 7 numbers. Letter D is where it starts to get a little bit tricky because there are zeros now involved. However, these zeros are sandwiched between 2 significant numbers. Therefore, if they are sandwiched, we know they're significant. Therefore, this is a 4 significant figure piece. Then we come to 10.3002. All those numbers are sandwiched as well. This is just 6 significant figures. Letter F, same deal. Even though there's no decimal place this time, these numbers are sandwiched. Here's where we start to get a little bit more complex. When we have a decimal place, we only start counting after we hit the first significant number. So all these zeros before we hit the 7, they don't count. This number, 0.00000075, only has 2 significant figures, which would be the 7 and the 5. And we reach this same conclusion with the next number, next letter H. This only has 1 significant figure. The reason for this is because these 2 leading zeros do not count towards significant figures. So take into account a couple of really big takeaways here. The sandwich numbers don't count as significant, and any leading zeros do not count as significant either. All right, so now we can move on to our next slide where we look at a little bit more complex numbers. We have 0.003003. Now, you're probably having your head spin here, but really we can take care of this no issue at all. We just don't count these first zeros here. The zeros that are sandwiched between the 3's, those are significant. So this number would have 4 significant figures. Just as before when we were talking about what the rules, 0. Sorry, any zeros coming after, let me start that again. any zeros that come after a decimal and don't have a significant number after them don't count either. This number is 3. And we also have the letter C, which has a bunch of zeros after that decimal point, and none of those are significant either. None of them count. And then we have letter D, which is 100. 100 because it has a decimal point. This is really important, this last one. Right here, letter D, because it has a decimal point that comes after those zeros, that counts as kind of a bookend, and it makes those zeros significant. So actually the number 100 with a decimal place after it has 3 significant figures. However, the 100 after it does not. This only has 1 significant figure, which would be the 1 according to our significant figure rules. One way we can make it have more significant figures is if we added a decimal place, it would have all of those be significant. Now we come up to 302. Those zeros at the end, there's no decimal place. They are not significant. So there's going to be 3 significant figures there. And we also have letter G. This last 0, it's not sandwiched between 2 numbers. It is not significant. And we only will have 3 significant figures here, which would be the 1, the 0 that is sandwiched between the 2 numbers, and the 5. So this is the final slide of our independent work for Unit 1, Lesson 2. If you need any additional assistance, reach out to your instructor. They're more than happy to help you. If you need any questions answered, please send an email or leave a Google Classroom comment on this assignment. Thank you very much for your time today. I hope you have a pleasant lesson. And once again, if you have any questions, make sure to reach out to your instructor.